All right, thanks, Anna Maria. Is the microphone close enough here that people can hear? Yeah? Up? Okay, is it possible to control the volume somewhere? Apparently I haven't taught in here before. Ah, here we go. That better?
Yes.
Yes, okay, all right, good. Okay, I learn something new every day. All right, so like Anna Maria said, I'll be talking about quantum optomechanics today. This is sort of a list of the different topics I'll talk about over the next 3 days or so. So I'm an experimentalist, and so I was told this should be sort of a mix of experimental data and explaining things a little bit more slowly. In general, all of these topics are going to sort of fall under the category of not making a quantum computer, but somewhere within the quantum information sort of domain. And so to elaborate a little bit more on what I do, so in general the experiments that we've undertaken over the last 4 or 5 years really have to do with controlling motion of different objects in a limit where it allows us to either, say, create pure states of atoms or control motion of mechanical systems so that we can couple them to optical or electrical fields. And over the next couple days I'll try to give you a flavor of some of these different ideas. And in particular, day 1 and day 2 will sort of be coupled together a bit. There I'm going to be talking about quantum optomechanics. Today I'll focus on a particular problem related to quantum limits to continuous displacement detection. So sort of a quantum measurement example that allows us to understand that a little bit better. That'll lead into some of the work we're doing trying to transduce states between a microwave, superconducting qubit, and the optical domain. And that quantum transduction, we actually will end up using a mechanical element to try to do that, which is a little bit odd, and I'll explain why it is that that's a useful thing. So day 1 and day 2 will sort of be coupled by a machinery that's sort of a weak nonlinearity. So in these systems, it'll sort of be like nonlinear optics applied to these particular cases. So it'll be all pretty much in the domain of Gaussian states. But it's useful to understand from a perspective of metrology and also this idea of transduction. It's fine to work in that limit. And then day 3, or somewhere around there, we'll see where things get. I'll talk about ultracold atoms, a little bit from a qubit perspective. So the title I'm putting there is not quantum computing with neutral atoms because people aren't really close to making a quantum computer with neutral atoms, but there's certain aspects of what we've developed in the ultracold atom field where we can start to look at those atoms a little bit more from a qubit perspective. So I'll talk about interfering, entangling bosonic atoms, how we make single atom sources in the neutral atom domain, and some different examples of how we can create Bell states with neutral atoms. I think you already had the lecture on ions, right? Okay, but not yet superconducting qubits. Okay, all right. Okay, so for today's outline, to start I'll talk about the basic interaction and cooling of a moving mirror in a cavity, which is basically the idea of cavity optomechanics. And this sort of corresponds to thinking about interferometers, or it does correspond to that. And I'll talk about example optomechanics experiments, give you a little flavor of the field. Then I'll talk about this problem of continuous displacement detection and utilizing squeezing for metrology. It's sort of an old problem and it has a little story that goes along with it, so I feel like it's a useful thing to present. This will sort of be accompanied by a general discussion of quantum noise and measurement and amplification, which is a broader theme. But this sort of interferometer problem is a particularly good place to look at some of this. I'll talk about some of our experiments that actually look at some of these continuous displacement detection limits. And then this will all lead into tomorrow, where I'll talk about quantum transduction. And it's related in the sense that I'll talk about optical readout today, sort of measurement at quantum limits. And the sort of question tomorrow will be sort of, can we optically read out the force of a single microwave photon? So if we create a single microwave photon, it affects the mechanical element, could we read that out in a way that's useful? And that's this problem of quantum transduction. Okay, so the basic system that we'll talk about pretty much all day today and tomorrow is shown by the little cartoon that's up there. So that's an optical cavity, and it has light inside of it, and you can imagine that one of the mirrors of that cavity is actually compliant. Okay, so it can move, and it is in a regime where actually the radiation forces from the light in that cavity can actually push on that mechanical element and actually cause it to move in a way that we're expecting and not do bad things like heat up the mirror or these sorts of things. So that radiation pressure force has been seen in a variety of different contexts now, sort of different effectively moving mirrors, and these are a variety of different objects that people have been able to have radiation forces having a significant effect on. And none of them really look like your typical mirror. They're all much smaller than a typical mirror or have some construct that allows them to sort of integrate a cavity with that type of idea. We'll end up using a particular mechanical object that looks like this, oscillates up and down like a membrane. There are also electrical analogies to what I'm talking about, and that'll become quite important as we talk about the transduction experiments tomorrow. But for the most part today I'm talking about optical light, 1 micron wavelength, actually pushing on mechanical objects. And I have these titles up here. Light controls micromechanical motion controls light. Obviously the mathematical description of the system implies both of these, and it's useful to think from both of these perspectives as we go along. Okay, so I thought what I would do is for the actual optomechanical interaction, sort of walk through a little bit what that is. It allows us to sort of go through the machinery of actually understanding what is the coupling in our system and in what limits our way. Okay, so the basic interaction here is just that we have a force on this mechanical element, and that force is going to be proportional to the number of photons that are in our optical cavity. And this G here is this is basically the relationship between that number of photons and the force. And so you could actually write that as the change in the cavity frequency per position displacement. And the number of photons is A dagger A for, we're going to use A pretty much the whole time here, or I'll try to use A the whole time for the cavity mode, the annihilation operator for the cavity mode. So if that's the force, then our interaction Hamiltonian is going to be h bar g, A dagger A, and then times x, which I'll break into a 0-point motion for our unitful thing, and then the x operator, then I'm going to write as, in terms of for the mechanical mode, I'll use b, and again I'll try to do that all the time so that things stay consistent. And over here, let's see, oh actually, oops, yeah, and then I can write this as h bar times a little g times A dagger A x hat, where that little g has incorporated that 0-point motion into there, so it's a more useful quantity to throw in as we go along. All right, so if I think about the total Hamiltonian here, I have the cavity mode, the mechanical mode, and then my interaction here. All right, and my G is my coupling constant. And in this I am now neglecting for the moment all driving or decay or all the other components that I would need in order for this to interact more broadly. And I think tomorrow I'll talk a little bit more, when we talk about transduction, a little bit how you understand input-output theory in the context of these type of cavity experiments. That's a nice way to sort of shape what I'm talking about tomorrow. For the moment I'll omit the driving and decaying. But what I did want to do is consider the point that in these experiments I'm going to think about the cavity mode as being a strong classical drive that I'll indicate by an alpha here, plus a fluctuation, this delta A, that is going to be the only quantum thing involved. And we're going to, this alpha ultimately is stemming, stemming from a large input field, okay? And so that's going to be quite large compared to this. The reason is that in these experiments, the G there is actually very small. Okay, so a single photon has a very negligible effect on these mechanical elements. We wish it could have a really large effect, but it doesn't really at this point. So we always pretty much linearize about a pump. All right, so if we do that, yeah. XZP, 0-point motion, the square root of h bar over 2 am omega m. Yep, so a scale for the 0-point fluctuations of the mechanical element. And in fact, in a moment I'll go over sort of what those scales are for our experiments. Okay. All right, so if I put in this sort of large classical alpha plus this fluctuation, what do I get? And I'm just going to look at the interaction part of the Hamiltonian, and there's other things that happen to other parts, but we'll ignore those for the moment and just sort of get a sense of what happens here. Talk about more complex equations tomorrow. So we have alpha plus this delta A okay, and so we're just going to go ahead and multiply that out. And maybe I'll describe the terms as we go along. So that first term there that just has an alpha squared, that's actually not going to be so important for what we're doing, because this whole thing is just going to be an average radiation pressure force, so we don't really have to worry about that. This guy here, the cross term, we have this expression here, and this will actually be what is most important as in this sort of linearized limit. And our third term here, that's delta A dagger. Now this is the term that in the limit of this always applying a large pump, this is smaller by alpha. Okay, so it's very standard procedure, but when I've gotten rid of this last term, you could say I've gotten rid of everything that's really sort of maybe of interest to a lot of you. So I've gotten rid of the large nonlinearity, but nonetheless, I'm going to keep the weak nonlinearity, and we're going to see what we can do with that. Okay, so let's assume that alpha is real valued for the moment, so we can sort of simplify things here. And so then I would write this interaction part linearized okay, and what is this? It's basically coupled oscillators. Okay, so you can see there's a symmetry between the mechanical mode and the optical mode, and we're going to then talk about, I'll just tell you sort of how I think about what terms of this are important in different limits. So this pump that I'm putting in, I haven't really told you about how that works yet, but I can detune it with respect to an optical cavity mode, and that pump has this amplitude alpha. And different things will happen depending upon that detuning, namely the detuning of the laser with respect to the cavity. So if I'm red detuned, so delta equals minus, not mu, minus omega m, then actually the important term will be this, A dagger B plus A the dagger. And that in general is referred to as a beam splitter interaction. Yeah.
I'm sorry, I forget. I think on the last slide you replaced A with this alpha plus del A.
Yep, that's right. Or I did that in the first step on this. Yeah.
Does that preserve the commutation relation?
So it should, with alpha in the limit of a large classical field.
Alpha is just a real number.
Alpha can be complex here.
Oh, I thought it's just a number.
Yeah, it's just a number. Yep. And then notice it just comes out over here, right? So it's just a number right there in this linearized limit. So I get this beam splitter here in this particular limit. And I haven't told you where this came from, but it's just giving you a sense of the type of interactions that I can get here. I can also talk about on resonance, where delta would be equal to 0. And then I would just write exactly what I had up there before, but sort of in a way where you can see that I would describe this as basically an interferometer. So I'm just measuring a phase in this case. And this is the limit that we'll look at a decent amount. Then we have the blue detuned limit, delta equals omega m. And okay. And this is known as a two-mode squeezing. And so this gives us a sense of the type of things we can do. The beam splitter basically allows us to swap photons and phonons. Yeah.
What is omega m? I understand delta is just a difference of your frequency.
Yeah, right. So the, yep. Okay, so this was, if I go back to omega m, the first time I showed it, it was here. So it's the frequency associated with the mechanical mode. Yep, so this is the object on the spring has a certain resonant frequency. And so we're going to assume that mostly it's moving at that frequency. And I'm talking about ultimately, we'll talk about this interaction a little bit more, but detuning the pump with respect to the cavity by different frequencies compared to that resonance, and we'll do different things. Yeah.
So here are we assuming that the line width of these resonances is relatively small, or does it also apply if kappa is close to omega? Right?
Yeah, exactly. So the one thing that I haven't indicated here, right, is something about this the line width, the kappa, and these will only be sort of well-resolved different interactions in the limit that kappa is small, some resolved sideband. And we'll talk about that in a moment as well. Okay? Yeah.
So I guess now these little a's are commutation relation must be like 1 over del squared in order for the commutation relation to be preserved. Is that right?
Let's see.
Del A is just the operator.
Oh, that del a, that whole thing.
That the whole thing's an operator, yeah.
Oh.
I could have put it prime, or I just wanted to differentiate it from A.
I get it now.
Okay, good. All right. Okay. All right. So hopefully this was useful to sort of orient ourselves. So those are the basic interactions. The beam splitter might be what I would do to exchange photons and phonons. I can do squeezing. I can create squeezed light. I can create correlations. I can make an interferometer and understand it and understand the quantum noise in that perspective. I can't make non-Gaussian states. All right. So people have been able to achieve this interaction in a limit where quantum noise is important over other things in a variety of different systems. So these span from sort of nano objects with really small masses to sort of room scale objects or LIGO type objects. And the frequency scale also spans a wide range. And part of the point of this plot is that this interaction can apply to all of these different systems, and there are different reasons that I might be interested in different domains. So the nanodomain is certainly useful in the context of if I want to get as close as possible to this limit where maybe a single photon would have a large effect on the mechanical element, then I might want to use something nano. If I want to detect gravitational waves, I want something with big mass, and so I want to be over here. The experiments that I'll talk about today are actually sort of in this intermediate regime here, and there are also reasons why you might want to be in that intermediate regime. There are certain things that we want to do where we want to separate different size scales of, say, superconducting circuits versus optical light in different places, and also just the sort of mechanical isolation that you can get here is often better than the nanoscale. So there's different experimental reasons to be in different regimes. So our particular experiments that happen sort of building over involve mechanical devices that look like this. So that's a drum up there that is made of silicon nitride. So it's a very thin sheet of silicon nitride. It's sort of 500 microns on a side, and it's 50 nanometers thick. So you can really see it with your naked eye if you look at it, but it's very thin, so it has a somewhat small mass. So the mass of these objects is on the order of 10 nanograms or so. And so instead of putting this object as the end of a cavity, we actually put it inside of a cavity that allows us to sort of separate the goals of controlling the light and the goals of controlling the mechanical motion, but effectively the interaction is the same. Moving this gene changes the resonant frequency of the cavity. Okay, and the sort of characteristic frequency of these things is on the order of 1 megahertz. So if I calculate the 0-point motion, that'll give you a scale for these type of problems. And so the 0-point level here turns out to be on the order of 1 femtometer. And we can compare that to maybe other physical systems that you've heard about. The ion traps, typically the 0-point motion is on the order of tens of nanometers. And this is a femtometer scale, so it's a more serious interferometry. Though larger scales of motion than, say, LIGO. It's detecting at 10 to the minus 18 meters. All right, so let's talk a little bit about the idea of what I'm going to call resolved sideband cooling. And now we'll start to talk about the cavity density of states and its effect on our ability to control the mechanical motion. So referring to the question over there. So let's say that I draw my cavity line shape looking like this, where this is frequency in this dimension here, and then I imagine that into this cavity I'm going to inject some light, and that light that's injected in the cavity will have some particular detuning with respect to the cavity resonance. So I'll draw that here as, say, this tone here. And I'm actually going to red detune with respect to that cavity resonance. And if you know about AMO physics, for example, you often cool atoms by red detuning with respect to atomic transitions. We can do a sort of the analogous thing here by red detuning with respect to this cavity mode. And so then if I imagine that my mechanical element is going to put some sidebands on this tone, I'll have a sideband over there, and I'll have a sideband over here. And I'm drawing this blue sideband is larger because the cavity has a larger density of states there. Now these sidebands, to be more specific, they'll be separated by the mechanical frequency, this omega m. And if I draw this sort of ladder of states over here, what this is representing is the distance between these two pairs is the optical transition, and the mechanical splitting is represented by that distance there. And if I were to sort of draw the cavity line width on this diagram, it would sort of show up as a width of these features here. So, yeah. Okay, yeah, what am I cooling? So what I'm going to cool is one particular degree of freedom of this mechanical object. Okay, so if I just think about the Brownian motion of this object, I'm going to reduce that Brownian motion. And actually, it's a cold damping process, so I'm going to damp it and also cool. Yeah, so when in laser cooling as well, sort of what I'm doing is I'm applying the right forces at the right time in order to give some damping, right? And in that way, I'm going to reduce the amount of motion. And we'll actually see that we can actually cool to the ground state of this harmonic oscillator based upon this technique. So I'll talk a little bit about how close we get to that, and also the requirements on doing this, right? There'll be relative rates. Yeah?
Sorry, so the red and blue sidebands are from the hybridization coupling?
So they're just from these coupled oscillators. And I could think about this totally classically in terms of my mechanical motion is modulating the resonant frequency of my cavity. And so I'm getting sidebands on the light.
You might have mentioned this, but what's the line width of the cavity compared to the mechanical motion? Because it seems like it would kind of wash out those.
Yeah, exactly. So it depends upon the physical platform, and one of the points of these type of systems is that we have been able to get to a limit where the cavity line width, it depends on the experiment, but in our experiment, the cavity line width is a megahertz and the mechanical frequency is a few megahertz. And that turns out to be resolved enough that we can cool pretty well. And that will actually come up in the next slide here. Okay, so let me talk a little bit about sort of these different transitions and what they look like on this diagram here. So if I imagine I start in this state here, and this green transition here would correspond to that guy there, and then I would think about sort of anti-Stokes, if you're used to that language, is represented by the blue. And then if I think about the red sideband, I can think about this guy here, and I would often call that the Stokes transition. And so what's happening here is because of that cavity line being narrower than the mechanical frequency, I can have a large asymmetry between those two processes. And when I have that large asymmetry, that can actually lead to this cooling process. There's many ways of thinking about this, but this is one of them. And so if I were to describe actually sort of the strength of each of these processes, the red one is reduced by the cavity response function. That actually comes from a factor that involves the mechanical frequency compared to this kappa. And I didn't show exactly where that came from, but that's from the typical response of the cavity. And as with any harmonic oscillator, I have this factor that's the Bose enhancement there, but the +1 for going up. And then for the case of the anti-Stokes, it will be proportional to just the occupation n. Now to use a notation that'll become important later when we talk about spectral densities, if I think about the radiation force and its fluctuations as a function of frequency, I can think about sort of an asymmetry in that noise process that will be different at different frequencies, and that's one way to understand what's going on here. And that ratio will be that mechanical occupation +1 over Nm, and that'll actually be related to the temperature. So I'm not deriving that here, but we'll use the spectral density notation later, but we can think about a spectral density of force noise and how in this quantum case I have SFF of omega m is not equal to those force fluctuations at minus omega m. But you can pretty much see what's going on from just that picture up there, that there's an asymmetry, and this can lead to a cooling process. So there's some requirements, though, for that cooling process to work well. So with atoms or ions, you're often in vacuum, and so you're not connected to other things that could heat you up in principle, though you're connected to your trap, which can be a problem. And so in that case, you are thinking about some cooling rates, but you aren't as worried about heating rates from your solid state environment. For a mechanical object that's actually connected to some solid state bath, let's think about sort of what the relative rates are. So we'll actually have sort of an optical measurement rate, photon-phonon exchange rate, cooling rate, sort of all of these terms apply to this particular rate. And that will be proportional to, there's actually a factor of 4 in there, but then also the number of photons that you're using, that I'm going to refer to as alpha squared here, and the coupling between the mechanical element and the cavity, which remember was that prefactor in the interaction Hamiltonian that we were writing down, and divided by kappa, the line width of the optical cavity. Now, in order to really understand how this works, we need to understand sort of the interaction with the propagating photons that are heading into the cavity and that kappa here, but I'll just write this down for the moment, where again alpha squared is equal to n. So if I want to make that measurement rate or cooling rate large, typically that means I need lots of light in the cavity to get large radiation forces, right? And I also want a large coupling, which remember is the 0-point motion and then how much my cavity changes with the position of the mechanical element. Okay, so I want both of those to be large. Now, when I want to be slow is the thermalization rate of the mechanical element to its environment. So, and I'll refer to that as, say, gamma thermalization, and that will be the number of thermal phonons in the environment times a mechanical line width, and which that mechanical line width is going to be inversely proportional to the mechanical quality factor. So if I put some energy in the mechanical element, how long does it take for that energy to go away? And that is also related to the reverse process of how long is it going to take fluctuations to move into the mechanical element. And then this n thermal is just my thermal energy scale compared to my mechanical frequency in some large temperature limit. Okay, so often in these experiments we'll actually work cryogenically where we start at low temperatures. And that's one way in which we make that slow. And so that means we often want a high mechanical quality factor and a cold bath. So these are the type of things that we work for experimentally in order to realize these type of limits. Okay, so one thing that we can look at now is actually cooling of this mechanical element, and maybe, given some questions, I'll maybe show this particular slide first here. So the square missing there. If we were to look at the phonon occupation of the mechanical mode as a function of this optomechanical damping. So we pump this with more and more light, and then we look at the temperature of the one particular mechanical mode that we're interested in, which is a fluctuation of this drum that looks like this. And we're just thinking of this as a harmonic oscillator, and we're asking about its occupation. And these bars are supposed to be on top of the ends there, not floating above them. All right, so we have this n bar, and then it decreases as we get to larger damping, and we can reach a limit where n bar is about 0.2, which means about 80% of the time it's in its ground state. And the limit here that we're running into is exactly what we would call the Regal sideband limit, which has analogies in atomic physics as well, and it's related to exactly this fact of what is the ratio of how well can my cavity pick out these different sidebands. And this data is from our experiments, and it shows that we can get pretty cold down to this expectation, and we can put a lot of light in these mechanical elements even when they start at cryogenic temperatures and they don't heat up. So to look at a little bit more carefully how we get this information about the occupation of this particular mode, what we do is we actually look at the fluctuations that we measure corresponding to that mechanical motion in the frequency domain at these two different sidebands, this red and blue sideband. And we can look directly at both of those in heterodyne detection. And we expect that when we're haven't cooled very far, that actually the blue will be quite a bit larger than the red, just because of this cavity enhancement effect of the blue compared to the red. But then when we cool far enough, we actually find that they come into equilibrium with each other. And that is actually corresponding to, if I look at those equations I had before, so to start, this term is dominant. But as I get cold, this one actually becomes quite important, and they'll actually come into thermal equilibrium. And you actually can sort of think of this as a back action limit to the cooling. But it means that we can control these mechanical elements fairly well. Yeah.
And coming back to your equations when you control the red, means that also the blue is changing, or just the red, when you lower the temperature, it reaches the limit that relative to the blue is?
Yeah, so the let's see, okay, on an absolute scale, what is one compared to the other? So N mechanical is changing as well. So if I were to look at the total area under those curves, it would be changing. Now there's also there's damping occurring too, so the amplitudes are a little hard to parse in that way.
So is this limit kind of circumventable through some clever techniques, or is it very fundamental?
So this limit is, if I were to just do this experiment, one thing I could do is in the experiment I could make my cavity narrower. And so it's not fundamental in that way. It's very experimental. And then there are tricky ways of thinking about, even if you weren't resolved sideband, but you had access to all of the information in the system, could you do tricky things in order to do better? And there are some ideas like that as well. Yeah. Okay. All right. So that gives you a sense of what we can do with these systems, how we cool them, and the sort of coupling that can occur. And that same coupling will come in some of these other discussions here. So I'm now going to switch to talking about the same interaction, okay, but just from the perspective of a different problem. And that problem is more from a problem of measurement. So let's say I ask, how well can I measure the motion of some object, and what are limits to that going to be? And so this is now a picture of a LIGO-like interferometer. So the experiments that we do down the hall really have nothing to do with detecting gravitational waves, but it's a good example of how we can think about quantum metrology being useful, and sort of the history of the problem as well. So in LIGO, this is a very schematic picture. There's two test masses, a Michelson interferometer, and you can tell the relative path length of those two paths by looking on your photodetector, right? And so you get a fringe that varies as lambda over 2. You sit somewhere on that fringe, either the dark port or somewhere on the side of the fringe, and then you look at variations in the amount of optical signal you get as you're looking for one of these test masses to move a little bit. So it's a very sensitive optical interferometer. LIGO aims to detect sort of 10 to the minus 18 meters. So one limit that's useful to think about for this, maybe useful is the wrong word, but people have thought about for this interferometer, is in a limit of a really strong probe. And that would be a case where radiation forces could have a large effect on these masses. And so it's sort of no longer an immutable structure. And this limit was thought about in the 70s in the context of sort of instabilities that might occur when you put a lot of light in and you can get a lot of forces on these mirrors. But another question that was asked was, what is the effect on the signal to noise if you also have radiation forces in addition to the quantum noise, the shot noise of the light that's in the cavity? So will radiation forces combine with the fluctuations of light to obscure the motion? And so this was a question that was asked early on, and indeed it turns out to be that it does obscure the motion. And there's a paper from around that time that's sort of useful to look at the abstract of. It's called Quantum Mechanical Radiation Pressure Fluctuations in an Interferometer by Carl Caves. And it talks about interferometers being developed to detect gravitational waves, and sort of the birth of the understanding of beam splitters and a lot of quantum optics can be understood in the context of this question of, does quantum radiation pressure fluctuations disturb mismeasurement? They definitely do, and this abstract says so in a nice way. And so what's the sort of basic idea of this? Well, from a physical standpoint, if I have shot noise in the cavity and then I have forces on the mirror, there's fluctuations in those forces, and that will actually drive up my mirror and obscure the motion that I actually want to see. Now, we can also do a sort of back of the envelope calculation that might tell us about this in the context of back action in the measurement. So this is very much a back of the envelope calculation that I can do, and we'll sort of see as we go along in what ways this calculation is a good starting point, but as we do the full analysis, it doesn't really tell the full story. So the basic way this back of the envelope calculation goes is, let's say I want to measure my mechanical motion to some delta x at some initial time. Okay, so let's say originally measure to delta x, and I'll actually put a measure on there to be very specific, at some time t. All right, so the idea of this back of the envelope calculation is really a sort of Heisenberg microscope type argument, where he was thinking about things like how well could I detect the position of an electron in a real microscope, right, with a certain numerical aperture. And if I say that I measure to that delta x measure at that time t, my momentum will be uncertain to what I'll call delta p perturb, right, that I would expect has to be greater than or equal to h bar over 2 delta x measure. Okay, so my sort of typical Heisenberg argument. And the important thing is if I want to measure this mass and say I want to measure a passing gravitational wave, I'm going to have to measure it at multiple times. And so that's going to be important to think about sort of at a later time what happens. Okay, so I have my delta x then at a later time that I'll call t prime, and that's going to be my initial fluctuations delta x as a function of t, plus something that is taking these momentum perturbations and turning them into position, right, as a function of time. And so I would write that as h bar times t prime minus t over 2m delta x of t. So now I have one term that's linearly proportional to this delta x, and then one that goes inversely. And so there's some optimal delta x that I'll get, and that I'm going to call that delta x at the standard quantum limit, and that'll turn out to be 2h bar t prime minus t over the mass. Okay? So if I wanted to think about this problem, and I wanted to think about, okay, will this standard quantum limit end up being a problem? Well, I could throw in a mass, a characteristic time scale, and an h bar. And early on, people did this, and they found that scale wasn't really far from where they wanted to be in, for example, in LIGO. Okay. All right, so again, this is very back of the envelope, and as we go along, I'm going to show sort of if I really treat this in the frequency domain in terms of spectral densities and take into account everything that's going on, then we'll paint a picture that's a little more complex than this. All right. And I think we'll start going ahead and doing that now. So if I think about this problem I was just discussing, if I put more and more light into this interferometer and radiation forces become prominent, then what do I expect to see? So what I'm going to plot here, in fact my x has disappeared here, I'm going to plot a quantity called the spectral density as a function of frequency. And that spectral density I'm going to call SXX, x just being the coordinate that corresponds to this mechanical motion that we were talking about before. So the units of this spectral density are meters squared per hertz. It's the thing that experimentalist always measures when they look at, for example, a spectrum analyzer. And so I can look at what I expect to see in a frequency domain. And pretty much all the plots that I'll be showing in the next while are going to be exactly in this frequency domain. So in the limit where I don't have much radiation force in the system, I would expect far in that limit I just have a white noise that corresponds to shot noise that's in the interferometer. And so I have something like the green line that's up there, even without that bump on it. And then as I increase the power in the interferometer, I beat down that shot noise. And note that this SXX is really in position units. I originally am measuring something that's a light out of the cavity, but then I use a calibration to change from those light units into the mechanical motion units. And eventually what I find is that I can actually drive up my mechanical element, and I get this large peak over here, and that corresponds to this back action that I was talking about. And so in terms of some terminology, we'll think about this position spectral density as being a combination of what I'll call imprecision, that I'll refer to in terms of I, and then a back action force that I'll refer to as SFF. Now that force spectral density, that's the same thing that I was talking about before when I was discussing we can understand this cooling process in terms of the asymmetry of that force noise as a function of frequency. All right, and in general, if I want to think about the effect that force noise has on the mechanical element, I have to take the mechanical susceptibility and multiply it by that force noise. And the mechanical susceptibility is this function here. I'll write it in its complex form that we'll use later. That omega m is the same. That's the resonant frequency of the mechanical element that we were talking about early on. M is the mass, and this is a complex function. And I think before I used capital gamma m to refer to the line width of the mechanical system, and an omega there. And this omega here is exactly this frequency coordinate there. All right. So basically, these force fluctuations are filtered by the mechanical response. Yeah.
Yeah. I might have just missed something, but it's not entirely clear to me why the noise spectral density goes down.
Mm-hmm.
I would expect that if your signal to noise was increasing, that your noise spectral density would stay the same, but that peak would just grow. So did you elucidate that a little bit? Yeah.
Okay. So I think the thing to clarify here is what this peak is. So there's another peak in the problem, which would be I'm trying to measure something, right? And that thing that I'm trying to measure, if it's a displacement, would have a certain height on this that would stay constant. And this is also on a log scale, so things are strange in that way as well. But this peak here actually corresponds to the back action that's increasing as I increase the light intensity.
And it's increasing resonantly because...
Right, because it's being filtered by the mechanical response. Yep. Okay, so this is always the noise in the measurement, and then I'm always trying to measure something on top of it, so smaller is better. All right. So chi m is the mechanical susceptibility. So I can then plot this. Again, this is SXX. That seemed to have disappeared. Oops. Whoa. No. Okay. Let's put that x in there just to be clear. This is still the position spectral density and as a function of probe power. So looking at the peak of this response, I see that I can beat down shot noise, but then back action will play some role. And if I then consider what is the total noise that I add at this optimal point here, then I'll actually find that if I'm on the mechanical resonance, I'll add a noise that's equivalent to the mechanical zero-point motion, okay, for this 2-quadrature mechanical measurement. Before I go back to that point, I can also consider the fact, and this will be important if we want to think about, for example, how LIGO thinks about quantum metrology. If I don't want to measure on the peak of the mechanical resonance, but I want to measure over here. So if I want to measure a force, it's not really such a good idea to be measuring over there because the mechanical response isn't as large. But if I want to do a wideband force measurement or I want to measure displacement, like in LIGO, then I might want to be measuring over there. In which case my back action curve would actually look like this, and the shot noise and the back action would cross at a different point, and that would be down here, and that would actually be less than the mechanical zero-point motion, and we'll come back to that later. But this fact that in this case I can calculate this just based upon, I put photons in the cavity and I calculate, given all the fluctuations, what do I expect? And I find that the added noise is equal to the zero-point motion. I'm adding a half a quanta of noise when making the 2 mechanical quadrature measurement. And that's a sort of very general rule that's useful to keep in mind. And so maybe we'll talk about that a little bit. Let me first label a little bit just in terms of these quantities that we've talked about. So we have the imprecision and then our force fluctuations there. So let's talk about added noise for a 2-quadrature measurement. And I don't know exactly what people's context for this problem is, but there's, I'll say a couple of different sets of things that you might have thought about. Homodyne versus heterodyne measurement, phase-sensitive amplifier versus phase-insensitive amplifier, 2 mechanical quadrature measurement versus single mechanical quadrature measurement. All of these problems have a sort of common underpinning of how I think about this situation. And like I said, I could calculate this curve here from just putting photons into the cavity, calculating through the whole thing, seeing what I get, but I can also have sort of some general rule that tells me, okay, I should never be able to do better than something, and from the non-commutation of the mechanical quadratures. So I'll attempt here to do a little bit of a derivation of this idea based upon a theorem that really comes from thinking about amplifiers. So anytime that I want to think about detecting, in this case I'm detecting this mechanical motion, somehow I have to amplify it to some level that I actually measure it. And if I think about then the system as just really generically in terms of an amplifier, then I could write the following. So let's say I have my 2 quadratures, which I'm just talking about 2 quadratures of anything, not really necessarily mechanical motion at this point. Let's just call them AS for signal. Okay. Oops. Okay, so if I have the commutator of x1 and x2, I'm going to say that's I over 2. I put a half in there because that eventually gives me factors of 2 that I'm more used to. So I have this commutator there. And now let's imagine that I'm going to amplify that signal. And I'm going to end up with a y that's some gain factor that I'm going to call square root of g1 times x1, and some other y2 that's the square root of a gain factor times x2. So now if I consider that I have these y's, this y1 and this y2, and I take their commutator, well, I should expect to get I over 2. But I'm not going to be able to do that if I have these gain factors here, unless I add that there could be some fluctuations that are added in the amplifier. Okay? So I'm going to call those fluctuations f. And it turns out that, and let's just write over here, if I consider the uncertainty product for x1 and x2, then it's going to be delta x1 squared, delta x2 squared, greater than or equal to 1/16, given all the various 2's that I've thrown in there. And over on this side, you can actually, based upon looking at all these different commutators, you can end up implying that if I look at sort of a normalized uncertainty product for these y quadratures compared to these gains, that's a prefactor here times 2 minus 1 over g1 times g2, that quantity squared. And if I stare at this for a little bit, if my gain is 1, then that's okay. Then I just have the same uncertainty. If my gain is really large, so those g's become really large, then I actually end up adding a factor of 2 to each of those uncertainty factors. Okay, so this is a really super simple, dirty derivation of the Cave's house theorem is what it's called. And so this says that when I plotted this guy over here, the fact that I'm adding a mechanical zero-point motion in this measurement is not surprising. Okay, and so that's something you should expect to happen. So let's talk a little bit more about actually measuring these noises, and then I'll talk about this quantum limit of adding a half a quantum of noise and this comparison to this standard quantum limit. So this noise of the radiation pressure that corresponds to shot noise of light in the cavity, we can actually observe in the experiments. And it's difficult to get to a regime where you can actually observe it because often you have to put a lot of power into these systems to get enough radiation forces, and bad experimental things end up happening before you do that. But these are some early data seeing that we could actually see an increase in this peak that's like that green peak that was on the other plot as a function of putting more laser power into the system. Okay, and another thing that can become important in these systems, let me actually get some water here. Any questions recently? I think I skipped pretty quickly between those different slides, but okay. So in these type of experiments where we have this radiation pressure noise, we can actually see it driving up the mechanical motion that obscures that motion. But there's also an interesting correlation in the system in that radiation pressure will actually is on the amplitude of the light. It's going to drive the mechanical element, but then that mechanical element is writing back onto the phase of the light in the cavity. So you can actually get a situation where the amplitude of the light and the phase of the light become correlated. And if you are in that situation, then what you can have is actually squeezing of the light. And this is data showing a situation where we're measuring the light at the output of the cavity in a homodyne detector. So homodyne detector, again, means I'm beating the light that comes out of the cavity with a laser that's at the same frequency, a local oscillator at the same frequency. And so if I look at the power spectrum of that light as a function of frequency in a particular domain where I've gone to the trouble to sort of mix those two quadratures, then what I see is actually I can get fluctuations that are below shot noise. The shot noise is shown by the green curve there. And this type of squeezing has a historical name that sort of comes from this same era as when we were talking about the gravitational wave detection and the different quantum limits, and it's called ponderomotive squeezing. And squeezing in general is a pretty good way to tell sort of how well the measurement efficiency in your system is doing. So this squeezing here is about 1.7 dB, which is pretty small. 10 dB is the best that people have gotten. This will actually correspond to getting light in and out of, actually in this case, a dilution refrigerator with an efficiency on the order of 30%. And this will come into the quantum transducers that I'll talk about tomorrow. So this squeezing of light can be important in thinking about these quantum limits and how you get around them. So let's go back to sort of the picture of these different quantum limits, keeping in mind our sort of most fundamental recollection, which is that if we're measuring two quadratures, we're getting information about both of them, then we have to add a half a quantum of noise. So this is now that same plot as before, except for in a frequency domain instead of as a function of power. And it's a funny frequency domain because I put it on a log scale, but it becomes a little easier to see what's going on. So the different things on this plot, and they're color-coded the same as the other ones. So we have the 0 point is this yellow part here. And then I'm picking a particular place on that sort of power axis to make this plot. And that corresponds to a sort of back action limited situation. So the green is larger because I picked that particular point. And then the gray down here is my shot noise. That's white as a function of frequency, just like in those original plots. So these are the different components that we'll add together to think about what is the noise and the measurement that I'm trying to measure something on top of. And one thing you'll notice is that because we have this mechanical response function, my back action and my 0 point motion drop off. And so if I take the sum of these two, then I get this dashed blue line. And that dashed blue line will correspond to what is the added noise of my measurement as a function of frequency, if I'm making this measurement. Okay. And often when you look at this type of physics in the literature, people either talk about this limit here, where I'm measuring on the mechanical resonance, or they talk about this tail over here that corresponds to a LIGO-ish type measurement, just for your reference. And in between, I think it's also just sort of interesting to understand. But let's first sort of compare this to what it looks like if I look at a LIGO noise budget. So remember, LIGO's big interferometer corresponds to the sort of physics that we're looking at here. We look at the displacement noise as a function of frequency, and the red is what they actually had for a noise in the actual signal run. And the blue corresponds to what I would expect from just fundamental quantum noise. And so you can see it's flat here, goes up here. That's exactly this kink in this plot here, flat here, goes up here. And this going up over here actually corresponds to the optical response. Okay, so it would be flat if you didn't have that. And you can see the shot noise limited in this regime over here, and haven't really gotten to a point where the radiation noise is important. Okay, so gravitational waves were detected even without seeing any of this radiation pressure noise that was such a big deal early on. Okay, but it is predicted that they're really going to push this down, and ultimately this will become important. What is really the focus of true LIGO improvements based upon squeezing is really dealing with the shot noise over here. So the squeeze light that's been used in LIGO so far is really related to that shot noise part. Okay, but if you really want to deal with this kink over here, where you have this balance of radiation pressure noise and shot noise, then you have to think about the tricks that we've been talking about. Okay, so let's go back to this plot here. So if we measure with our homodyne detector in the sort of typical way I would measure, yeah. Yeah, right. Yeah, so this is so in LIGO there's a certain optical cavity structure, and this is the filtering from the optical cavity structure. So it's not white because of that. Yeah, I don't know exactly what defines that, but it would be white if it weren't for that structure. Yeah. But yes, otherwise I think that this plot should be accurately representing what I would worry about in LIGO over here. Okay. So if I then think about, I measure in my typical way, and that's really what the standard quantum limit means, that standard part of it. I should say a little bit about standard quantum limits. So there are many quantum limits, and a number of them are called standard. Okay, so there's a number of standard quantum limits, and not really all of them are limits. And so it's really a misnomer in many different ways, but I've defined for you the particular limit we're talking about, and it really corresponds to a case of I put in a coherent state into my interferometer, and I measure it in homodyne detection at the output. Okay, all right, and this is what I would expect to see for the added noise in this case. So then if I think about now at every single Fourier frequency, I optimize my optical power to measure as well as I can. Then I would actually, this would be the standard quantum limit at any particular Fourier frequency. And this sort of line out here corresponding to the standard quantum limit is really what historically people have thought about in the context of these sort of broadband displacement measurements. Now we can look at this plot here in the context of if I were to do that calculation I did a little bit ago and say that I'm making a 2 mechanical quadrature measurement and what is the best that I should be able to do, then that actually would not be this blue line here, right? It would be a line that actually follows the 0-point fluctuations here. So I should only have to add a half a quanta of noise in an ideal measurement of this situation. So there's many ways that people have thought about getting around the standard quantum limit. One of them is actually to do a single quadrature measurement instead of a 2 quadrature measurement, and I won't talk about that here. But a sort of one message that I think could be useful in this talk is that these two curves are not the same, and what is the distinction between them? And what is some way that I could think about actually measuring below the standard quantum limit and getting to this limit that I really think I should be able to get to? And one way of thinking about that is that in the standard configuration, I really just have not set up my detector properly. And there's, I think I put it, okay. In a bit, I have a reference to a particular review article by Osh Clark and others that talks about quantum noise and measurement. And one of the themes of that review article is really about how I think about quantum noise, but also how do I set up my detector correctly. And this is a particular example of how to think about that. Okay, so we did this back of the envelope calculation too of this standard quantum limit. Here I'm showing you it in more glory here. So what can I do to actually do better that corresponds to setting up my detector in a better way? And one thing that I can do is actually just rotate this homodyne detector so that I'm mixing the phase and the amplitude quadratures. Okay, so in that way, I actually introduce the correlations that I want to introduce in order to measure better. So if I rotate that homodyne detector to 25 degrees, then you can see I do better in this particular part of frequency space. And that's actually something we can do in the experiment. Now, there's an idea that's existed for a long time called variational readout, where you would actually imagine for any Fourier frequency, I would optimize my homodyne detector to measure as well as I can. And if I do that, then I can measure better over a larger range of frequency. Okay. Now I can also see this in the context of this as a function of probe power plot, and sort of trying to summarize this in this sort of illustrated guide as well. So if I think about my usual measurement, I have the sum of the shot noise and the back action, and this would correspond to the standard quantum limit, but I think I should be able to do this well if I'm making a 2 mechanical quadrature measurement. And if I rotate my homodyne angle, indeed I'm able to go below that line. Oops. Okay. All right. So let's do a little bit of analysis to understand a bit what's going on here in the context of, I've talked about these correlations, how they come into our squeezing measurement, and so how do I think about this in terms of all the different factors that I've talked about? So if I think about my total noise in the position spectral density as a function of frequency, I could think about certain mechanical contributions. Those might be the residual thermal noise or other things like this. And then I would have my imprecision that I won't write as a function of frequency because that's just white in this idealization. And then I have the same term that I wrote down early on, which is I have my mechanical susceptibility multiplying this force fluctuation, this SFF. Now what's key here, and this is sort of foreshadowed in this sort of showing you this squeezing, is that also we have a cross term that represents a correlation between the mechanical object and the thing being used to measure it, the light. And so I have this mechanical susceptibility times what I'll call SIF, that cross correlation. And let me write down what this mechanical susceptibility looks like again. Okay, so this is a complex function. On mechanical resonance, then I actually just have this term here, right? And so that whole thing is imaginary. And so I actually will find that that correlation actually doesn't have a big effect on resonance. But off the mechanical resonance, it does. And so I find that that correlation term becomes important. So what I can do is I can introduce correlations by either injecting quadrature squeezing or by using the squeezing that already can exist in the system via this ponder motor squeezing. And if I do that, then I can get rid of some of those correlations and I can get back to sort of more of an ideal detector situation. And that's sort of what's going on when I'm able to vary my homodyne angle and actually measure better. Okay. All right, and then, oh yeah, and here's the citation that corresponds to sort of this larger viewpoint of how I think about measurement in these cases. All right, so let me show you some data that shows that we can actually measure things at these quantum noise limits, and we can do these things like change how our detector is detecting and see that it detects better than how you would standardly to set up the detector. So these blue data points are showing this idea of the standard quantum limit. So if I increase my probe power, then I beat down the shot noise, but then I have radiation pressure noise that becomes important. And the different curves here correspond to measuring at different Fourier frequencies with respect to the mechanical resonance. So like I showed before in that plot where I drew the red line, is that it seems like I'm doing all, really lots better by going off mechanical resonance. But really what I'm doing is the mechanical susceptibility is worse. So if I were measuring a force, I wouldn't be doing as well. But I'm able to also, if I go off mechanical resonance, the thermal contribution will not be as important, just like the 0 point is farther below. But I can see this effect, and I can see it over a wide range of frequencies. And if I think about the shot noise limit, that's actually this dashed gray line here. And in our experiments, we actually don't get all of the information out of the system. So in quantum measurement, of course, getting all of the information out is key. We get a large fraction out, and that allows us to see these effects. We have an efficiency of 35%. And that number will actually become important tomorrow. So this is actually taking light into and out of a dilution refrigerator to measure this, okay? Because we start with a mechanical element that's very cold. And I'll talk more about that some more tomorrow. But what that does is, because we're only measuring at a finite efficiency, we can only do so well compared to an ideal measurement. All right, so what we can show in these experiments is if we look at these curves that correspond to the position fluctuations of our mechanical element, and we rotate this homodyne angle, right? So we're not measuring in the phase quadrature, but we're mixing some amount of amplitude fluctuations and phase fluctuations together. Then we can see that the red curve there corresponds to measuring better on this side of mechanical resonance, but measuring worse over there. And so you can see the correlations are helping us in some part of frequency domain and hurting us in other parts. So then we can look at this in the context of this sort of standard quantum limit plot where we're changing the probe power and we're looking at this position spectral density. So the blue curve is just like one of the ones that I showed you earlier, and then the red ones correspond to when I rotate my homodyne angle. And I can see that I actually measure better here and worse here, given this effect. And it's a small effect, but it's actually showing measuring below the standard quantum limit. Now this particular method of mixing amplitude and phase is maybe not really the best way to do this ultimately, in the sense that you're really throwing away information when you mix the amplitude and phase quadrature, because you really want to get all the information about the mechanical motion, which is in the phase quadrature, and you're sort of throwing away some of that information. So in that way, I'm not doing as well up here. But nonetheless, because of the correlations, I actually end up doing better down here. We can also show this idea of the fact that the homodyne angle that I would ideally set my detector to will actually be dependent upon frequency. And in how people have contemplated actually employing this technique, they imagine putting some cavity or something in the arm of the interferometer to actually vary that phase as a function of frequency. Here we actually just varied it by, we did one experiment where we set the homodyne angle at one value, then we did another experiment where we set it at another value, and then we saw where it was optimized. So we can see that we want to set the homodyne angle to a smaller value here. Ideally on resonance we would set it to 0, and then a larger and larger angle as we go farther away.
So you're plotting this versus frequency?
Yes, that disappeared there. Yes, this is omega minus omega m. So the frequency with respect to the resonance of the mechanical object. That disappeared in other plots too? That one was probe power. Yeah. And then this guy here is the same thing. Except for my subscripts seem to have disappeared in various iterations. All right, that's also a m, so this is omega minus the mechanical frequency, and this is on this weird log scale, right? So 0 is over here, the resonance of the mechanical response. And that, of course, corresponds to the place where you would most like to measure forces.
And we're all in blue between red because that's where we get this.
So red and blue, by detuning everything the appropriate amount, I could do what I want in either domain. I tend to think of blue because in LIGO I actually think about being higher than the mechanical resonance, but in either case. Okay. Yeah, but that's definitely just only a half of that picture. All right, so that's the idea of variational readout, and that I was showing by that red curve there. Now, there's also, for some future reading, if you care to think about this problem, there's a citation down here. I can actually use more complex local oscillators than a single tone local oscillator. I could actually imagine using 2 local oscillators, and some recent work has shown that you can actually think of that as a way to effectively make a single quadrature measurement, not by stroboscopically varying the light in the cavity, but actually by changing your detection, by changing your local oscillator. So that's something to contemplate if you want, but I think we won't go into that. All right. So, any questions about that part? So again, the theme is, if I want to measure something, I should think about my detector and how I've set it up. So I think with that, I'll move on a little bit to talking about these mechanical elements and how well we can really control them. So going back a little bit to things that were more towards the beginning of the talk. And this will become important, so like I said, next time we'll talk about quantum transduction in the context of using these mechanical elements as an intermediary. And it's going to be very important that those mechanical elements are low noise in a variety of ways. Low noise meaning coupled to the sort of bath that we want them to be, and in terms of really controlling the spectrum of mechanical modes. Now that was important for the last measurements that we're making as well, but we're really trying to push that in the context of the transduction. So this topic is quite experimental, but it has a very ubiquitous name, which is called thermal noise. And it shows up in LIGO mass suspensions, it shows up in precision reference cavities, it shows up in the context of these type of measurements. And let me start out by talking about a problem that's not so related to the particular experiments we do, but related to the experiments of, this is data from actually Junier's group. I think you'll hear from him maybe in a week or two. But in these experiments, what they want to do is they want to make the quietest reference cavity possible. And it'll turn out that the Brownian motion of the mirrors at the sort of extreme levels that they want to reference their laser to will actually end up hurting them in terms of the ability to stabilize that laser. And what they care about those at low frequencies, there's many, many different modes of these mechanical structures. And you can think of them as sort of I think of them in frequency space out here as many modes, and then there's many tails of those many modes. And those tails, they will add up more if you have low Q mechanical materials. So if you have a very sort of lossy mechanical material, then you'll actually have this tail grow large, and that will give you actually more noise in your reference cavity. So this little cavity picture there is them making a cavity out of crystalline materials, and those crystalline materials give higher Q peaks to these resonances and give a more stable reference cavity. So we have a little bit of a different problem, but the same ideas still apply in certain contexts. So we sort of live in these forest of modes out at high frequencies when we're trying to control one particular mechanical mode and say cool it. But we still care about those modes, how well they couple, if they're high Q, and whether we can control that mode structure. So one of the things that we actually do in our experiments is we create periodic arrays of masses in order to control the acoustic radiation that leaves our mechanical elements. So remember, our mechanical element that we care about is a really thin drum of silicon nitride. And it really is a drum, and I'll talk about this a little bit more at the beginning of next time. It's pulled really tight, and it gives, if I weren't to pull it really tight across a substrate, it would have sort of kilohertz resonant frequencies, but I then pull it really tight and it has megahertz resonant frequencies. And what I can do is, this blue stuff is a silicon structure that is holding on to that drum. And that silicon structure here has a periodic array of masses, and that scale is on order of the scale of the wavelength of the acoustic radiation. Okay, so for silicon like this here, the speed of sound is something like 3,000 meters per second. And then if I think about the frequency scale involved, sort of megahertz frequency scale, then if I pattern this on a millimeter scale, that corresponds to what I would actually need to control that radiation. And we can see in this plot here, if we were to just make a silicon chip that didn't have this patterning, then we would have this blue mode structure here. And it looks like a mess, but really all of the different peaks that are involved in that structure are really individual mechanical modes of this slab of silicon. And the red here corresponds to, if we do put this crystal into the structure, then what we find is these regions here where we've sort of pushed the modes away. And so